Okay, so in reading this problem, we said that it's frictionless and that so far we've gotten that it says a spring of force constant 2,250 newtons per meter, which I listed down here in the diagram. It also compresses the spring 0.3 meters from its equilibrium position, which means when it's unstretched and uncompressed, before coming to rest. So it's going to end up compressing this thing, this distance x, which is 0.3 meters, at which point it will be stopped, probably changing direction, about to be launched backwards. So in this, you can see here it has like A, B, and C, but it gives a ton of information about this ending point. So the more information I have about a location, the more that makes me want to use it potentially as a point in our conservation of energy equation. So like, what do I want to use as my 2 points before and after? I can use like A and B, which a lot of people did, right? You figure out what is the speed when it encounters this friction. I can go from A to C. I can go from B to C. Like I got to pick 2 points, right? But this I guess fourth one is of particular interest to me because I have a bunch of information at that point. So I'm going to add that in. And actually, that's what I'm going to use because point A has a lot of information. I know that the speed is at rest at this point. I know the height, right? Nothing's happened with friction or anything yet. At the end, friction's taken some energy out. And I know it's stopped. I know the K value. I know how far it's compressed. So A to D calls out to me as the 2 points to use. Okay? That's what I'm going to use. Otherwise, if you went from A to B to get the speed, and then you went from B to D, why don't you just go from A to D? What did that, they eliminate the middle step with that. We're trying to figure out the force of friction. So I'm going to start by writing out the conservation of energy statement or the equation, which gives every single possible energy that we can have. And then we're going to go through one by one and double check if it's there, or if it's not, we'll slash it up. Doesn't matter what order you put those in as long as they're all there. It's sometimes nice if you have multiple instances to choose for your before and after, like we do here, to just indicate that I'm going from point A to what I'm calling point D at the end.
Sir Bonner,
Yes.
does it matter if we use A and D, not B and C?
So the question is, does it matter, for people in the classroom, does it matter if you're using the 2 points, because friction is only acting from B to C? But as we go from points A all the way to D, that happens within those 2 points. So we can still look at that as I'm going to show you in this example. It still happens between points A and D, meaning friction is going to take energy out as it travels over this little interval. Okay, so that should become apparent if you just hold on to that. I'll come back to the question if you still have it. This first term says from points A to D, is there a force that acts along the distance that it moves? That would be like along this entire thing. And I'd say, yeah, there's, other than force, gravity, and spring force, there's this frictional force. And so that's going to tell me to diagram it. So I would say, did you diagram X and F? If you didn't, that's going to really help you with this work thing that we do, okay? So it's going from point B to C. And notice I'm going to draw that as an arrow. That identifies that this, I don't want to use X because X is for the spring, so I'm going to pick a different letter. I'll use like D. That's going to mean that D is positive. Then frictional force is going to point this way. And I'm trying to figure out what that's equal to, but that's going to definitely be negative because it's the opposite direction of the way it's going. And knowing that work done by any force is equal to that force times the distance over which it acts means that for friction, the work done by friction is going to be the force of friction times the distance over which it acts. If D is positive and friction is negative, that's going to give me negative work done by friction. Okay, if they are same direction, then a negative times a negative is a positive work, or a positive times a positive will give me positive work. So it's easy to figure out mathematically if you have positive work or negative work by looking at the arrows for the distance and the force. for that problem. So diagram those arrows really helps you to identify it. We can furthermore interpret this positive or negative work as being a gain or loss based on that sign. So if it's a positive work, that means that that energy, that force is changing, is going to be lost. Positive is lost. It's opposite what you think. Negative is gained. So in this case, the negative work done by friction that we have would imply that that energy is taken away because it's gained. I mean, like that friction is acquiring that energy, right? It's taking that energy for itself. So it's gaining it. So I'm going to write that down then as a negative work, not just done by some force, but done by the frictional force. Okay. The next one that we're looking at is gravitational energy. So at point A, does it have a height above its lowest point? Gotten a lot of questions over this one. And the issue is, where is the height 0? And you can define that differently in every problem, which almost makes it more confusing, right? So like if I have a block and I put it on top of the desk table here, you would say it has gravitational energy because it's above the floor, right? What if we're on the 3rd floor in like the math classroom? You know, can I still do that and just say it has gravitational energy because it's above the floor? But we're on the 3rd story. So do you see how confusing this gets now? So really what I would say to keep it easy is just pick the same height to be 0. And if you're not sure if you use like where the dirt is on the ground, or whether you use the classroom floor, or whether you use like the tabletop, like where am I calling my height 0? Use the lower of the 2 points that you're looking at. So in this case, we're looking at points A and D. Are they at the same height? I'd say no, D is the lower one, right? So make that height 0. Right? If we went from B to D, that's the same height. So then make them both at 0. And then there's no gravitational energy. You see what I'm saying? So in our example with the block on the tabletop, if I never move it other than from the tabletop to the floor, then it doesn't matter from the 1st floor or the 3rd floor or whatever, right? It's irrelevant. So just use the floor. Wherever is of the 2 points you're looking at, where is the lower one? Which one's the lower one? And then make that the height of 0. So that would make this my height of 0 right here, which means that this is starting off 3 meters above it. So yes, we have gravitational energy. At part A, when it's up here, there is a spring, but it's not compressed. So it's not storing any energy at that moment, and it's not moving because the speed is 0. At point D, it's at the height of 0, right? It's at my height of 0, so there's no gravitational energy. There is a spring that's stretched, in this case compressed, I guess, and it's momentarily stopped at this location as it changes direction. So that's going to equal the elastic. A common question I get is why is this work term here, this work done by force, why is that only on the left side? Why isn't it on both? That positive or negative sign will assign it to the right side or left side. Meaning like if this were a positive work, it would stay on the left side. If it's a negative work like this, then in making it positive by adding it to the other side, it's going to assign it to the right side, meaning it's going to end up with that energy. It doesn't start off with that energy, it ends up with it. So that negative will mean gain, which forces it to line up on the ending points side. So rewriting this, we get gravitational energy equals elastic energy plus the work done by the force friction kinetic. If we interpret what's happening here from an energy transfer standpoint, the energy that it has in its gravitational height at the beginning is going to be lost to stretching or compressing the spring and whatever energy friction takes away. And that's what this is mathematically saying. You see that works? So we don't want to get caught up in like, so is that always true? Is it always going to be gravity equals elastic plus work? No, it's not always true. What always is true is this conservation of energy statement. It's just the slashes are different from problem to problem. So you can't like just like make a generalized claim of like, okay, so I just got to match up this situation with the future one. No, just go turn by turn and it'll be a lot easier that way. So approach every problem as its own problem. I'm going to expand these now. Now we can get going a little bit faster. Gravitational energy is equal to mgh. Elastic energy is 1/2 kx squared. And then this wants to know the force of friction. So work done by the force is equal to that force times the distance over which it acts, which would be D. It's not over the entire distance. It's only over from B to C. And subbing in values, we have 10 for mass, 9.8 for gravitational field. Our initial height above 0 was 3. We have 1/2. K was 2,250. Our x is 0.3 meters. We got to make sure we square that. Force friction we're trying to solve for, and then the distance is 6 meters. If we do our algebra correctly, we should get 32 newtons. Technically, that should be a negative because friction is negative, but I'll just get the absolute value here as like a number value for the strength. Is there anything I can go back over? Or did this like trigger a question or something more general? Sam, yeah.
I got negative in my answer. That's not wrong. It's like I end up getting like negative 32.1, like that.
I don't know if it should come out to be, he's asking if it came out to be negative, is that wrong? I don't know how you get a negative from this because there's no negative signs. Did you leave this as negative over here? Like, did you leave this as like negative force friction kinetic times 6? Then that could be the same thing then. That's okay. I mean, technically I should divide out, but I don't know. But otherwise, with the way I have it set up here, you wouldn't be able to have any negatives. But it's okay. That would be correct. No questions in this one? Moving on. Each of these problems showcases a different potential pitfall for you guys of what you can get confused on. So they're each valuable in their own way. This one has a weird like grams and centimeters, and it's like kind of a strange situation, but we have a ball that's hanging on a string. So I'm going to draw this to try and visualize what's happening here and start listing out things I know. The mass is given as 100 grams, which is 0.1 kilograms. We've got to get that done right away. It's initially moving with some speed of 0.3. That's in meters per second, so that's okay. And it's going to be lowered to some distance below it. So that's going to mean that our distance is, I measure from the middle of the ball, I guess. The distance is going to be from the top down to where it is in the bottom. I can call that X. I can call it H. I can call it D. I mean, it's just the distance that's moving. So we can call it X. I'll call it H for now, but you can call it X. It's not a problem. It's just naming. But that equals 0.5 meters. And it's going to slow to rest. It says it stopped. So that would mean that the ending speed down here is going to be 0. So let's write out our conservation of energy statement because that's what it says to do. And then we're going to solve for tension. I realize it's kind of annoying to have to write this whole thing out, but it does save you from potentially missing a form of energy when it should be there. And it only takes about 7.2 seconds on average to write it out. So it's not like it's that big of a deal. So we'd be looking at this and saying, is there a force acting on a distance? Why don't we draw it out? Like, so the distance is vertical. So we're looking for vertical forces. There would be an upward tension and a downward force of gravity. If I call this height positive, meaning down is positive, then gravity is positive and my tension is negative. Regardless of what you call positive and negative, the height that is traveling down is opposite the direction of tension, which means you're going to have a negative work done by tension, negative work done by force tension. And pause there. Is there something about this I can re-explain? Opposing directions between height and force tension. In terms of gravitational energy, I got to define my height as 0. So you should be asking yourself, are you doing the same thing as me, right? So with work done by tension, it would be, are you diagramming the force and the distance? If you're not, and that's causing you issues with this, like identifying if there's a work done or what sign it has, then that would be the solution. And you can do that on future problems. You should be okay. On gravitational energy, if you're getting that messed up, you want to probably ask yourself, are you defining a height of 0 clearly? And if you're not, do that as well. So this is going to be my lowest point here, down at the bottom. So at the point at the top, it does have gravitational energy. There's no spring in this problem. It's moving in the beginning. Okay. At the bottom, it's at lowest point. So that means that gravitational energy is 0. There's no spring in this problem and it's stopped. So this is going to be all equal to 0. That maybe makes you a little twitchy because you're like, I don't like that. That's 0, but that's because this negative work done needs to get added to the other side, which means that the gravitational energy and the kinetic energy that it starts off with will be lost to the work done by force tension. I'm going to pause there. Other questions? Okay. In doing this problem, we have mgh then, plus 1/2 mv squared equals force tension times the distance over which it acts, which is h in this case. Remember, it's just like how far the force acts over. And this allows us to get tension once we sub in the values to be, I believe it's 0.99. That's written down. Yeah. Okay, so this next problem then, I'm going to keep going. This next problem has a bow and arrow. I'm just going to draw the bow, not the person or anything, but that's the bow. And then here it is stretched. So I'm going to try and draw the exact same thing for the bow, but it's going to be stretched like that. What I want to show here is that it's going from this position to this position. So it's being pulled back. So it's going from here to here. This is point A and this is point B, right? So it's getting pulled backward as you pull it back. This is my distance X, which is the 0.4 meters. Okay, so are there any forces acting along that? Because I know I'm going to have to ask that here in a second. So I'm going to diagram any forces acting left and right. I know that there's going to be a pull this way that I'm doing as a tension force. And then there's going to be the pull back from the spring force. If left is positive, because we want to make the distance that it moves positive, that means the tension is going to be positive, and that spring force is going to be negative. I'm going to write out the energy. Conservation of energy statement here. We just identified the forces that are acting left and right along the distance, and friction would be, I'm sorry, I keep saying friction. Tension would be a force that's acting along the distance. Since it's in the same direction as X, then that's going to mean it's a positive work that's done by force tension. It doesn't change its height. It's at the same height for point A and B, right? So there's no change in height. So we'll call that height 0, which means it's starting at 0. And it's actually going to end up at 0 as well. It's not changing its height. Elastically, there's nothing at the beginning. And kinetic energy wise, there is nothing at the beginning before it's pulled. At the end, when it's loaded, there is elastic energy, but it's not yet launched. So there's no kinetic. So this is one statement we get from conservation of energy. That's going to help us to answer part B, but that's not going to help us to answer part A. Okay, so what I want to do to answer part A is to do that spring force equation, right? So part A, which I'll put up here, we can use this spring force equation. We know that it's going to be at its maximum strength of 230 when it's stretched 0.4 meters. That means that K is going to be equal to 575. Now I can go to work done by force tension here and use the elastic energy of 1/2 kx squared to solve for it.
Mr. Bonner?
Yeah.
I know you said that so we use
Okay, so this is going to end up giving me then work done by force tension equal to 46 joules. Okay, I have an advanced thing that I'm a little bit hesitant about explaining because I don't want to confuse people, but one question that we could have would be, why can't we just do this equation to solve for the work done by force tension? There's nothing wrong with that equation. But if you get 230 times 0.4, you end up with, I believe it's 92, if we do that, right? Which is not our answer. Okay, so why is that wrong? Why can we not do 230 times 0.4, right? Because that's going to equal 92, which is actually double what we should get. Why does that make sense that that would be double? This is wrong, right? The value for force tension is not constant as we pull it over this distance. Do you see that? Because it starts off when x is 0, when you're not stretched at all, the force is 0. And as you pull it, the force gets bigger. So this equation that we have here comes from base times height. So if we had a force tension versus x and it were constant, then it would be a flat line, right? And then our area would be base times height. In our problem here, it's not a constant of 230 the entire x, right? It, as you stretch it, it gets bigger. So it's this shape, right? Where 230 is the maximum when it's at 0.4. So the work is 1/2 that maximum force times distance. Only because it's that triangular shape. So this would be correct, right? 1/2 base, which would then make this 46. Okay. So when can you do that? When is it like not going to work like this? You can use this equation when as long as you have constants, right? It's algebra. So as long as you have constants, you're fine. Meaning as long as it's a flat line if it were plotted on a graph. The only time we haven't had these flat line things are when we're dealing with springs like we are here, where it's like an elastic thing. Okay, again, that's a little bit of an advanced topic, but I just wanted to point that out in case someone had done that and was like, wait, why does this not work? Oh, wait, does physics not work all the time? We don't want to think that. Okay, we have one last one. To try and go a little bit quicker, since these are going to be a little bit repetitive, to save myself from writing it, I'm actually going to show the solutions to this one. This is in modules too, in case you want to follow along, but we have an object that's mass 5 kilograms. That's already standard units, so that's good. It's released from rest at point A, and it goes down this frictionless track. No friction is nice. That means there's no work done by friction. We want to know the speed at B, the speed at C, and then the work done by gravitational force. So let's start with A, the particle speed at point B. So what I've done here is I've written out the conservation of energy statement for points A to B. I know there's no...
You're not sharing your solution.
Oh, it's a different... I got to reshare the screen. Hold on. Thank you. Okay. So in doing point A to B, the lower of those 2 points I'm looking at is going to be the B, right? Because B is lower than A. So I'm going to make the lower point here B to be a height of 0. So I'm essentially saying that this is my height of 0 for part A. That means that the initial height of this thing at point A is going to be 1.8 meters above 0. If you did 5 as your height, that will actually work because you're defining your height of 0 to be down here. But that would mean that if you had 5 at the beginning, like it shows here, then you would also have gravitational energy at point B associated with this 3.2 height. If you subtract the gravitational energy of 5, and then you subtract that 3.2 from it, you'll get that 1.8. So it's the same mathematically, it's just extra stuff for you to do. So my way will be the simplest way in terms of if you just solve for, you assume that of the 2 points you're looking at, the lower of those two would be a height of 0, and then that's going to make it very simple to do, okay? But it's not that it's wrong. Hopefully you're okay with part A here and solving for the speed. If you repeat that same process, but we go from A, where I know a lot of the information, to C, then notice I'm using for height here 3, because if now I call C my height of 0, then A now starts from a height of 3 above that point. So that's going to be my new height, and that will give me a new speed at position C. There's nothing wrong with going from B to C, but that requires you then to have the potential energy of 1.2 and the initial kinetic energy based on your speed you just calculated. And then at the end, it would be the same thing you have on the right side. But that would still work. It still gives you the same thing. Okay. Then part C, a little bit confusing here because it's that, again, that work concept for people is tricky. So it wants to know the work done by the force of gravity in going from points A to C. So when I'm doing work, I want to show the distance. In this case, it's going to be a vertical distance, so we can call it a height. And that's going to be going downward as it goes from A to C. So I'm going to make that positive. My force gravity, which is what they're asking about here, is also in that downward direction. So those are going to give me a positive work done when I multiply that force times that distance over which it acts. My force gravity I found from the mass as 49 newtons. The distance is 3. That should give me positive 147, positive again because the arrows are in the same direction. I can interpret that as making sense because that would mean that gravitational force is losing that energy. So that change represents a loss, but that makes sense because we're losing gravitational energy. And that's what work done by force gravity is the change in gravitational energy. It's just strange because with work, we talk about that as being positive when it's lost. Okay, any other questions? Okay. We're going to be jumping over to the breakout rooms here so I can get